Hi, in this video we look at a problem in geometry that is solved using the closed interval method. The problem is the following. Find the dimensions of a rectangle with a fixed perimeter of p centimeters that has the largest possible area. The figure shows a rectangle with a perimeter of p. There are infinitely many such rectangles since we can make the rectangle very narrow or very large while the perimeter remains constant. We will start by introducing variables that define our rectangle. First, let b be the base of the rectangle. Second, let h be the height of the rectangle. But note that since the perimeter is fixed to p, when we fix the base, the height is automatically fixed as well. This is true since twice the base plus twice the height, so 2b plus 2h equals the perimeter p. So 2h is p minus 2b, and h is p minus 2b divided by 2. This shows that if we fix the base, then the height is the perimeter minus twice the base, all divided by 2. So the area of the rectangle, the function that we want to maximize, will be base times height, so b times p minus 2b over 2, and after expanding, this gives pb minus 2b squared over 2. To form a rectangle, clearly the base b is positive, and since p is the fixed perimeter of the rectangle, b cannot be more than half of the perimeter. That's because there are at least two bases that form the perimeter, so b is strictly less than p over 2. Overall, we need to maximize the area a of b on the open interval 0, p over 2. A is a polynomial, so it's continuous, but the interval is open. It would be nice if the interval would be closed. This way we could apply the closed interval method. So what if we allow 0 and p over 2 as possible values of b and maximize on the closed interval 0, p over 2 instead? When b equals 0, so the base is at 0 length, or b is p over 2, so the maximum length that it could actually take, we have extreme cases where the rectangles are not rectangles anymore, but line segments. Both have a side p over 2 and still a total perimeter of p. But clearly the area in each case is 0, so that's why I consider them as extreme cases. So we'll never have our maximum area at any of these two values of b, and we can safely include them in our interval. Now the interval is closed, and we can apply the closed interval method to optimize. We first compute the derivative of a of b to find the critical numbers. Now a prime of b is the derivative with respect to b of pb minus 2b squared over 2. Because the denominator is a constant, the derivative is just 1/2 times the derivative of the numerator. There's no need to apply a quotient rule here. So the derivative is that of the numerator, which is p minus 4b over 2. It is 0 when p is 4b, or when b is p over 4. So this is our only critical number. We now evaluate our function a of b at the critical number and at the endpoints. A of p over 4 is p squared over 16. Now pause the video if you want to look at the details of the computations. At the endpoints, we already know that the area is going to be 0. So therefore, by the extreme value theorem, the maximum is when b is p over 4. If we want to know our height, we're going to replace that value of b in h, which is p minus 2b over 2, and we get that h is p over 4 as well. So therefore, the base and the height are the same, and the rectangle is a square. So to summarize our findings, we could say that among all rectangles that have the same perimeter, the one that maximizes the area is a square. Thanks for watching.